Okay, so last class we looked at we kind of wrapped up Bandgap references, but there is one last thing we need to do, which we'll finish up in the first portion of today's class, and then we'll move on to output stages. So today we'll be looking at what is called the fractional bandgap reference. So far all the bandgaps we have looked at have had output voltages. I think at least the ones we looked at in class, the output voltage was somewhere around 1.2 volts. Okay. Now what do you do if your power supply becomes less than 1.2 volts? Let's say your power supply was only 1 volt. What would you do? Right? You obviously have a problem, because you expect all your op amps, all your circuits to operate at some particular voltage, right, at VDD, and if that VDD itself becomes smaller, it becomes a problem. Okay. So that's what we have looked at so far. So now what we are going to generate is, we want to generate something like this, right, some Vref over K. So in other words, we want to generate something which looks like this, or some multiple of this, it doesn't matter, right? So far we were taking VBE and adding some multiple of delta VBE, right? Delta VBE is of course PTAT. Okay. Now what we are going to do is, we are going to divide that, so we can just do the same thing, we can scale down VBE instead of scaling up delta VBE. Okay. And this one can be less than 0.4 volts. Okay. So this is fairly straightforward then, if we can do something like this. So let's first start off with the conceptual diagram, then we'll see, based on what we have looked at for the CMOS band gaps, we'll see what we can do. Okay. So first of all, let me call this I bias 1. This is diode 1. What is the voltage here? VBE1. Okay. I'll call this voltage Vn. So first of all, what is Vn? Vn is nothing but VBE1 times R3 over R2 plus R3. Correct? So I'll just call this VBE1 over K. What is VO? If this is Vn, we'll assume that the negative feedback makes this also equal to Vn. Okay. Then across D2 and D3, you have a delta VBE. Correct? You have VBE2 minus VBE3 to get to V0. Correct? So this is what you have. So now your V out is nothing but VBE by K plus delta VBE. So what you'll have to do is adjust K, of course. Then you need to adjust delta VBE. Delta VBE will depend on the saturation currents of D2 and D3 as well as the bias currents of D2 and D3. You need to adjust all of those parameters to make sure you get a temperature insensitive curve. Again, you need to take dou Vref by dou T and set that to 0 at some particular temperature. Correct? you'll have to do the same thing which you have done before. So this portion is the voltage divider. This one is your delta VBE generator. So of course you have the condition that these two guys have to operate at low VDD. Let's say less than 1 volt, but definitely less than 1.25 volts. Okay, so now if you look at all the, let's go back, most of our CMOS bandgap references have had this kind of architecture, right? Because you don't have easy access to NPN diodes, and this is fairly easy to straightforward to build. Okay, so let's see if we can come up with something like this in the case of a CMOS bandgap. So everybody got this portion? Okay, so we'll start off with the same kind of architecture we had before. One. So this is A. This is NA, okay, Q4, I'll call this K times W over L. This particular case, these are all W over L. And then we are going to add the voltage divider here. These are buffers. Okay, to make sure your PNPs can have very low betas. You don't want that to load your voltage divider. Correct? Okay, so let me name these VIN, VIP. I'll call this VX. I'll call this VY. So VY is the same as VREF with respect to ground. This is still a single-ended reference. And I'll call this VA and VB. Okay. So now we'll assume that R1 by R2 is greater than 1. Okay. And this is denoted by M. What is the current through R1? What is the current through R1? Minus VA by R2. Okay, but you don't know VA. Can you give it in terms of quantities we know? Preferably in terms of PBs or something like that. this voltage, this is also VA, right? So that is just VBE by R1, VEB by R1, correct? So VA is nothing but VEB1 times R2 over R1. Okay, so this is VEB1 by M. So this is your, first of all, as a fractional multiple of VEB. Okay, that is the first portion you want to generate. Now let's go back to the main circuit. So now we have found out VA. Okay, and from that, of course, you can also find out Vx. But now let's go back to your feedback circuit. You will assume that your negative feedback is going to make sure VIN equals VIP. Okay. Correct? What is VIN? VA plus VEB2, correct? So you have VA here plus VEB2, correct? Okay. Now VIP becomes equal to that through the negative feedback, and now you can write a similar relationship between VB and VIP with VEB3. VIP is nothing but VB plus VEB3. Okay. So VB is nothing but correct? So this is your delta VB you wanted to do, and of course note that these two currents are not equal. That is of course a prerequisite. That's why we made sure this was some K times this, right? Because you want to make sure the currents are not equal so that you have a delta VB across Q2 and Q3. Otherwise, if the two currents are equal, this will just become VEB again over M, right? Okay. Now you can choose M and Ks and everything such that this becomes temperature insensitive. Correct? I'll just write this. You can do this. So delta VEB is P tag, the other one is just a VBE. You can adjust the coefficient such that it becomes 0. Okay. VB is nothing but the voltage across R4. So now you can write Vref in terms of this value, in terms of VB. Okay. Correct? This is exactly what you wanted. So you have a fraction m, you can use R3 and R4 to get any voltage you want. Typically that may be 0.4, but you may want a slightly larger one, maybe 0.8 or something like that. You can adjust R3, R4, M such that you get the right value you want. Okay? So this is called the fractional band gap. Now, yes? VBG, band gap. Your original band gap was VEB plus some M times delta VBE. So we are just dividing that by M, right? The M factor will not change from what we looked at before and now. Did everybody get that? Okay. Okay, so the important thing is that Vref less than 1 volt is possible. Okay, and this has been proven. People have done like 0.8 volts and so on. Okay, 0.8, 0.6 volts has been done before. Okay. As promised, we'll move on to output stages. Okay, so the main idea for output stages is you want it to be linear, you want to have efficiency, because output stage you may need to drive a very low impedance load. Okay, so it needs to provide a lot of power, therefore it needs to be efficient, power efficient. It needs, of course, linearity is another concern, we'll come back to it maybe next week. Okay, but first let's start off looking at something very basic. So let's say, actually, yeah, this is fine. So let's say we take a MOSFET. We'll be looking at both, okay? We'll be looking at MOSFETs and bipolars as when we look at output stages. Let's start off with the MOSFET, okay? So let's say it has some bias voltage VB. This is some bias current, okay? Now you can think of three cases relative to the value. If you consider, so what are the parameters we are interested in? So of course VB is a parameter of interest, V is a parameter of interest, and of course the threshold voltage, okay, is a parameter of interest because it decides when the transistor turns on. These are the three voltages in the circuit which are of interest. Okay, output voltage will just be something times V. Okay, so we don't worry about that now. But these are the three voltages of interest. Let's say this was your VT. Let's say this was VB. VB should be greater than VT for the transistor to be on, of course. Suppose this V sin omega t look like this. This is V. Okay. So for the transistor to be on all the time, okay, you can get a condition between these three voltages. What is the condition? This is one way to put it, right? VB minus V should be greater than VT, right? So that at the lowest extremity of your input voltage, your transistor is still on. In such a case, okay, in such a case we say that the conduction angle theta is 360 degrees, because throughout the cycle the transistor is always on. Okay. Now, obviously now that we have done this, we can also think of other cases. What happens when you keep reducing this? Okay. What happens if you keep reducing VB or increasing V? Either way is okay. What happens? At some portion, it will start to clip, right, at the lower end. So now you also have what is called class B. So this one is called class A operation. Okay, when the conduction angle is 360 degrees, it's called class A operation. Okay, now you can think of class B operation. These are all like classic terms. Okay, class A, class B, it's just names which people came up with. If you choose VB equals VT, it look like this. So this portion M1 is completely off. So you bias VB, you make VB exactly equal to VT, the threshold voltage of the transistor. So that any time the input signal voltage goes below VB, the transistor will turn off. So it conducts exactly for 180 degrees. So half cycle. Okay. Then you can think of a third case when VB goes less than VT. That's called class C. And we'll also discuss the case when theta is between 180 and 360. We'll discuss that also. Okay. If you look at this, what you'll actually get. If you look at, let's say if you plot the current, you'll get a very, very small clip portion of the sinusoid. Rest of the time the transistor is zero. Correct? Okay. So what you'll find is when you have cases like this, these two cases, very obviously you will need the transfer function of the amplifier is nonlinear. That much is for sure, because you are actually clipping the sinusoid. Okay. In many cases you may need some kind of, of course, at appropriate frequencies you might be able to use some kind of filtering. Okay. There will be cases if in RF power amplifiers where you use similar kind of topologies and you try to filter the output of other harmonics. Because what happens, you have studied power electronics, all of you? No. You have done none of you has done even one course on power electronics. Okay. Have you seen this kind of clip waveforms before? Rectifiers, for example. Okay, in which course did you see that in rectifiers? In which? 12th standard you had rectifiers. Wow, okay. Things have advanced a lot, obviously. Okay. Any other course? Which one? Oh, I see. Instrumentation. Same. Instrumentation? No. Oh, the first basic electrical engineering. Okay. So all of you have seen these kind of waveforms before, where you have half sinusoids, quarter sinusoids and things like that. So if you are given something like this, will you be able to calculate the Fourier series coefficients? You won't have any problems. Okay. What is the bias current in this case? We have 180 degrees. We just have a half sinusoid. Anybody remember? Okay. So if you have a case, okay. So this one I have shown actually, I have shown the current, right? You have a half sinusoid, you have zero. It's cut off. Correct? I have shown the current there. If I tell you this is the current waveform, and I ask you to calculate the average value of the current. Average value is the DC current, right? Nominally the DC current. If I tell you to calculate it, will you be able to do it? Does anybody remember what this value is? Huh? 2 by pi. What is it? So this, let's say this is I. I by pi. Okay. So Find out. So some people say I by pi, some other you said 2I by pi. Okay, why don't you try to find out what the exact value is. I want you, this is your homework for today. Go back and calculate the average value of the current. Okay, two things, average value of the current and the first harmonic. I want you to calculate both. Okay, but definitely the fact that it has clipped waveforms means that it is nonlinear. You are inputting just a sinusoid. You will not only get the sinusoid, you will get some harmonics of the sinusoid also, right? So that's why that's another way to check that it's nonlinear. So in all these cases, so the parameters which you are going to trade off, gain, of course, because now depending on what this ID is, you will take the, yes, you no longer be approximately, sure, but what you have to do is, you can find out the gain for the first harmonic. What are you interested in? You are putting in a component at omega, right? Output you get omega, 2 omega, 3 omega and so on. But you are still interested in the component at omega because you are trying to build a linear power amplifier. Of course it's a large signal, yeah. So what? Okay. What will be the gain here of this amplifier? What you can, okay. So here is the thing. When you do this homework, when you find out the first harmonic of the current, that multiplied by the output impedance, in this case, let us say you had some RL, I mean you could have some RL here also, okay. That multiplied by RL, okay, would give you your gain, correct? Would give you your output voltage. Now if you divide that output voltage by your input voltage, right, you can, okay, so if you take the output current and divide it by the input voltage, you can get the nominal large signal GM. You no longer have small signal GM, you now have an effective large signal transconductance, right? You can still represent your gain in terms of your large signal transconductance. Now that is obviously, large signal transconductance will be a function of V. That much is for sure. But for every V, for every value of V, you might have a different transconductance. When, of course, no, you'll have, what do you mean by saying you'll have distortion? In this particular case, because if you just use a resistor, you will get a sine, plus you will get other higher frequencies. If you just had RL, okay, your output voltage will just follow your output current, definite distortion, right? You have clips. Suppose you put in some kind of filter here and get only the first component, first harmonic component of the voltage. Gain is varying with what? Absolutely, that's right. So what the capital GM you are calculating is what is called the effective GM. You can never use it in, I mean you can define it, say that this transistor has this large signal transconductance, but it is a function of VI obviously. Okay, and you are right, at every point it will have a different thing, and that is why we are calculating the overall effective thing, effective transconductance. Okay, this is useful in specific cases. This may not be useful. So this kind of using large GM may not be useful for calculating the gain of the stage, for example. Of course not. We just looked at this, right? We'll get this. Let's say if you look at a class B stage, you will get this. Of course, in class A, you're okay. First of all, we are assuming that this voltage is much larger. Okay, so first of all you can rewrite this guy. So let's look at, suppose you have to rewrite this equation. Correct? What is this? This is the overdrive of the transistor. If you just consider square law MOSFETs, it's just the VD sat of the transistor. Correct? So the condition is you're assuming that the voltage is less than the overdrive. Okay, you know that when you go to overdrive, when you go to VD-SAT, when the voltage, output voltage goes to VD-SAT, it starts to transfer, goes into linear region. You definitely have distortion problems. If you don't do that, definitely the conduction angle is good. If you make sure V is much less than VB minus VT, that amplifier will be very linear. The closer you get to VD-SAT, the more non-linear the amplifier will get. That is all. Is that clear to everyone? So the other trade-off is of course distortion, because now if you want to design an amplifier, VT you may not be able to change, but you can definitely change VB. Correct? You can change VB such that you have better distortion or worse distortion. So that is definitely a trade-off. The last one is the power efficiency. Okay? If you are trying to drive some large load, if you have several milliamps, tens or hundreds of milliamps, you are definitely worried about efficiency. That is, you are going to calculate the signal power and find out how much DC power you are burning to drive that much signal power. Okay? That will be a measure of the power efficiency. Okay, so let's start off with the class A output stage in the bipolars. We'll come back to MOSFETs later. Let's start off with bipolars. So let's say you have Q1 and Q2. Okay, and let's say this current was IC1, this current is I0, this is the bottom transistor Q2 is just a current source. So let us say the current through that is IQ, which is the bias current. Okay, the output voltage is VO. So let's start off with, so now what do we want to find? We want to find out, first of all, let's start off by finding out the input-output relationship between VO and VI. Okay? How do you find that out? Any ideas? I want to find out something like this, or at least some equation relating VO and VI, and preferably only device parameters. Correct. Okay, so let's try. So you want to write down. So first of all, you can write VBE1 is, what is VBE1? VT ln. So this is one relation you know. What else? VI minus VO equals VBE1. Okay, what else? You still don't know IC1. Good. IQ plus VO by RL. It's IQ plus IO. It's nothing but IQ plus VO by RL. Correct? So I'll rewrite this slightly. Okay, so this is your input-output relationship, correct? For very small signals, you know that Vi is approximately going to follow Vo, right? Vi should be equal to Vo for small signals, that you already know. Why? This is an emitter follower, which has a gain of 1. This is your nonlinearity term. Okay? So now we'll find out what happens to the output range. So now you know the relationship, input-output relationship. Now let's find out what are the limits, okay, to the output. Of course, if you keep increasing Vi, Vo will not keep increasing, right? One term will become more dominant compared to the other and so on. So let's try to find out what the limits are on both sides, when you keep increasing Vi and when you keep decreasing Vi. We'll first assume that Vo is greater than 0. Sorry, first of small mistake, small error in the because eventually we are going to work back towards the 741 output stage which we looked at. Okay, so this is VCC and minus VEE, not ground. Right? If Vo is greater than 0, Q1 is always on. Okay? In which case, we can find out what happens. So you keep increasing Vi, right? You can find out a relationship between across this. What is the relationship? This is Vo, this is Vi. I'll call this Vi max. Vi max will give you Vo max. What is the positive limit to keep increasing Vi? What is this? What is the positive limit? What happens if you keep increasing Vi? This is just a static characteristic, right? I'm just taking Vi as a voltage, I am increasing it. What happens? What happens to Vo first of all? Definitely Vo will also follow it, right? Hopefully linearly. Okay, then what happens? How high can you take it? VCC minus VBE base what? Okay, so I just call it VSAT. So the minimum voltage that bipolar transistor can sustain across it and still be linear, we'll call it VSAT. Right? It could typically be 0.2 volts, somewhere around 0.2 volts. What is Vi max? Correct? It's VCC minus VSAT 1 plus VBE 1. Correct? Note that VBE1 is somewhere around 0.7 volts, VSAT could be 0.2, so in reality your Vi max can be larger than VCC. Okay? So at this limit, Q1 will move into saturation. Okay. Suppose you consider VO less than 0. Okay. This is your VO. Let me just copy this figure. Sorry. So we'll go back to the current relation. IC1 is IQ plus VO by RL. Okay. Now, since now this is a function of VO, the IC1 is a function of VO, okay, and RL. So now you can actually think of several cases. What happens when RL is very large? The two cases will differ. Okay, we'll see this why. So first, let's assume RL is very large. Let's start off with that. Okay. In which case, IC1 will be approximately equal to IQ. That is, we are neglecting the VO by RL term. So the output current will be much smaller than your quiescent current. Okay. Vi min minus VBE1. What happens if you keep decreasing Vi? In this case, what happens if you keep decreasing Vi? So since IC1 is always equal to IQ, Q1 is good to go, right? There is no problems with Q1, right? And since you are decreasing Vi, VCE will always be larger than VCE sat also, because VO will definitely follow it to a large extent. What happens? Q2 will go into saturation. Okay? Correct? So Vi min minus VBE1, which is that's the same as VO, will become minus VE2 minus VE plus VSAT2. Correct? This will be the case when RL is very large. Okay. How about what happens when RL is very small? When RL is very small, I out can actually become very large. Correct? I out can become very large. And remember, now V out is negative. So you actually have current flowing like this, out of the load into the ground through Q2. Okay? And now you can have a case where Q1 can become cut off. IC1 can go to 0. When does that happen? When does it happen? Who was that? Oh yeah, what did he say? VO by RL equals IQ. Correct? Well, in this case it's mod VO by RL. VO is negative. So in reality it happens when VO equals minus IQ RL. And that's what you get from this equation, right? You set IC to 0. There is a chance for Q1 to go into cutoff. Okay, so this is VO equals minus IQRL. Now suppose you want maximum output range. Now when RL is very small, this tells you VO equals minus IQRL. Okay, that is when Q1 goes into cutoff, so that gives you one limit. Okay, but ideally for maximum range, you don't want to depend on Q1 getting cut off, because Q1 is what you use for the positive half cycle. You actually want the maximum voltage range will happen when Q2 actually goes into saturation. Okay, that is what you can actually sustain as far as the current source is concerned. So you are going to choose minus IQRL. So you still have to go with this condition, VO equals minus IQRL. But you already know you can go till, oh, this is VI min. This will give you a corresponding VO min. Minus VE plus VSAT 2. So that you are going to design correct? You are going to design choose minus IQRL equal to minus VEE plus VSAT 2. This is your design parameter. IQ is your design parameter. RL you don't have control over. You need to drive a particular load. So this is your optimum bias current. Okay. Now suppose you have to draw the transfer characteristic. V out versus V in. What will it look like? Anybody? Sorry? Okay. Okay, so let's say it starts at VSAT 2. Okay, so will it be flat or will it be, I don't know. So, did you mean like this, or did you mean it starts at VSAT 2 and goes up, or what? It starts at VSAT 2 and goes up. Okay. Does it go linearly or some other behavior? Initially non-linear, but then becomes linear later. Of course, you know it has to be linear around the origin. This is after all an emitter follower. It better have a gain of 1, right? And it should be linear. Okay. Does it pass through the origin? Definitely does not pass through the origin, because we know there is a relationship with VBE1. So definitely it crosses at VBE1. Correct? It crosses the x-axis at VBE1. Because when Vi is 0, correct? What happens then? Okay, so let me. Of course, if you decrease Vi below that, it flattens out. You cannot go below that, right? VO does not, even if you can decrease Vi below minus VE plus VSAT 2, V out will remain constant. What happens here? Correct.
So the non-linear term had VO and I equal to omega.
Correct.
And what goes in 0 is VI equal to VO equal to 0.
Can you have Vi equal to VO equal to 0 here? There is always, okay, so close to the origin, the transistor is going to at least have a bias current, IQ, through it, correct? So between Vi and Vo, you always have a VBE drop, correct? The gain, if you apply Vi, a small signal, you will get a large signal. You apply a small signal at the input plus a bias. At the output, you will get bias minus VBE and the small signal around that of gain 1. Okay, but right now we are not even talking about the signal. We are talking just the DC characteristics. Okay, we will find out how to figure out the signal characteristics from the DC characteristics. Right? I am sure you have done that before, but we will do that for all three cases, class A, class B and class C. What is the max value of V out? V sat 1. What is this value? Minus VCE minus VEE plus V sat 2. Okay? Okay. You can also have a third case. Of course, this is the case 2. Okay, if you don't choose IQ optimally, then you will just ramp out at you can also have that case. This case, the full red curve shows the optimal case. So this portion of the curve, will happen if you choose IQ optimally. If you don't choose IQ optimally, then it will just max out at minus IQ RL. That we have already seen. Okay. Okay. So let's stop here. We'll continue tomorrow.